Hey everyone, just going to continue with 3.1. So here we are. What are we on page 4? Yeah, that's right. Okay. This is some types of probability we're going to run through. There's 3 types: theoretical, empirical, subjective. Theoretical is also called classical, and it's used when each outcome in a sample space is equally likely to occur. Also, a good way to think of this one is it's the one that you can calculate probabilities without having any previous data. So it's usually all of your things like dice, cards, coins, and things like that, where you can use counting principles to calculate the probability. You don't need any data or experiments done. Empirical, on the other hand, you do need to have some previous data. It's based on observations obtained from previous data. Okay. We'll get to some examples in a minute. And then subjective is based on intuition or opinion, and that sort of thing. So usually it's in the wording, and it's also how the probability has to be calculated. So like number 5, what's the probability of being struck by lightning is 1 out of 280,000. Well, that's an empirical probability. I'm just going to use E for empirical, because you need to have some data on who has been struck by lightning, maybe how many people were struck by lightning last year compared to the entire population. Okay, you won't be able to do that in a theoretical way. Number 6, though, is theoretical, right? So I'll put a T for that one, right? Because we know how many sides are on the dice, that each side is equally likely to occur, and so we can calculate that. We can do the calculation without ever touching dice. Same with number 7 is also theoretical, because we know how many cards there are in a deck and how many aces there are. So we can do it without ever even touching cards. We can just theoretically figure out the probability. Number 8, however, Shaquille O'Neal making free throws, that is empirical, because we have to know what percentage he makes free throw shots. We need that data, that previous data, so that we can make the prediction. Right? The Mega Millions, that's again theoretical, because the lottery is based off of balls that are in these cages, and they crank the cage and out drops a ball, but each ball is equally likely to occur, but you can find the probability without ever having any experimentation done. 10, doctor thinks. I can stop reading there. They're subjective. Yeah, so as soon as you see that kind of terminology where somebody is making a prediction based on their subjective opinion, then it's subjective. Again, we're back to coins on number 11, so that's theoretical. And the identity stolen, we have to have some data, so that's empirical. Okay. Next, we'll get to some fundamental counting principles, or coming up next is some ways to do some counting so that we don't have to list every outcome in a sample size, and then we can find the probabilities based off of these counting principles. Blah, blah, blah. Let's look at some examples. Fundamental counting principle: if one event can occur in m ways and a second in n ways, the number of ways that 2 events occur in sequence is m times n. So you just multiply the 2 together. And that can be extended for any number of events. For example, number 13, you're going to purchase a new car. So there are 3 manufacturers, there are 2 car sizes, and there are 4 colors. How many different ways can you select a car, basically? Well, by the fundamental counting principle, that's 3 times 2 times 4. That's 24 ways. In other words, if we went and listed all of the possible different cars, we'd have a list of 24. One on the list would be a compact Ford that's green, right? Or we'd have a mid-size Honda that's white. All of those would be listed, and there would be 24 different cars. Okay? This can be applied to things like home security systems or passcodes, passwords, and that kind of thing. Here we have an access code for a home security system that consists of 4 digits. Each digit can be any number from 0 to 9. So numbers from 0 to 9, that means there's a total possible selection from 10 digits, right? Because not 0 is included. 0 and then 1 through 9, 10 digits. How many access codes are possible when each digit can be repeated? Okay, so think about how many choices you have for each digit. In other words, the first digit, well, I can choose from 10 digits, right? Anything from 0 to 9. My second digit can be any of those digits as well because they can repeat. My third digit, I have 10 choices, and my fourth digit, I have 10 choices. So I'm writing 10 in there because that's the number of choices I have for each digit. And then if I want to figure out the total possible number of access codes, I would multiply all those together based off of that principle, that fundamental counting principle. Multiply all that together, and we have 10,000 codes available. Okay. Now, what if we change it up a little bit? How many access codes are possible? The first digit cannot be 0, and the last digit must be even. Okay, so we might give some conditions on each digit. Okay, so now we go to that first digit. It cannot be 0, but it can be anything else. So then we have 9 choices for that digit. There's no restriction on the second digit, so I've got all 10 to choose from. Same with the third. And then that last digit has to be even. Even numbers are divisible by 2. We're going to include 0 as an even. So 0, 2, 4, 6, 8. That's 5 digits, right? So that one is, I'm counting them up, all of the even digits that I have to choose from. 0, 2, 4, 6, or 8. If I multiply all that together, 4,500 codes. Makes sense that it's less than that original 10,000 from the previous example because I have restrictions. Restrictions are going to result in less available codes. Okay, and that's the fundamental counting principle. We can use that counting principle to calculate some probabilities, like number 15. A probability experiment consists of a spinner, and we've got, what was that, 8 different digits, right? 8 values that we can land on, okay? And then we're going to find the probability of tossing a tail on the coin and spinning an odd number, okay? So we have a coin and the spinner. So when I set up my probability, I know it's going to be a fraction, and the bottom of that fraction is all of the possible ways that this event could occur. And I can use the fundamental counting principle for that because there's 8 possibilities on the spinner and 2 possibilities on the coin, heads or tails. So that means there's 8 times 2, 16 total possibilities. How many of those 16 possibilities result in tail and odd? Okay, well, there's 1 tail, and there are how many odds? That's 1, 3, 5, 7, 4 odds. 1 times 4. Okay, and then if I do my calculation, that's 4 over 16. That reduces to 1/4, right? Which I could do as 0.25 or 25%. Notice we accomplished that probability then without ever having to list the sample space. So it's a lot less tedious if you use those fundamental counting principle ideas, right? The other way would be I'd have to list all 16 of the outcomes and then hunt for the ones that are odd and tail, right? Like we did in a previous example. So this fundamental counting principle will save you time, especially when the numbers get really large, like if I had a spinner with 1,000 numbers on it, I don't want to have to list everything. Okay. Next, we're going to look at, and finally, we'll get to empirical probabilities. So empirical probabilities, there's a formula for it there. It's similar to the theoretical probability formula. It's the frequency of event E divided by total frequency. So let's take a look at some examples. Number 16, a company is conducting an online survey, how they read books during the past year, if at all. All right. So we had 1,490 adults surveyed, and then there's the pie chart. All right. What is if I go down here to the question, based on this empirical data, what is the probability that the next adult surveyed read only print books during the last year? Read only print books, there it is. Read only print books is 578. So there was 578 out of a total of 1,490. And then I would just grab my calculator and do that out. 578 divided by 1490. We're getting 0.388 on that. So about 0.388, round to 3 decimal places. So notice what you're doing there is you're making a probability based off of previous data, right? Or we're using previous data to make a prediction about the next person surveyed, right? That's the empirical idea. We have to have that previous data to make the prediction for what people tend to read and how they read. Okay, got another one here. We have a frequency distribution. We have 975 social networking site users surveyed. Okay, A, what is the probability that the next user surveyed is 23 to 35 years old? So 23 to 35 years old, there's 312 of them. So I would take my 312 divided by the 975. All right, where'd my calculator go? Here it is, 312 divided by 975, 32%. So I would just write that as 0.32, no rounding needed. It worked out to perfect 0.32. The next one, what is the probability that the next user is not, okay, not 36 to 49 years old? So 36 to 49 is right there, 254. But we don't want those, we want everybody else. So I have two ways I could do that. I could add up all of those other frequencies, right? I could just go this, plus this, plus this, plus this, add them all up. That's the longer way. Or I could use subtraction, right? I know there's 975 total. So maybe first I'll do 975, subtract 254. So 975 minus 254 is 721. That's how many people are not 36 to 49. So now I could take that 721 and divide it by the 975 and get an answer. Don't make a typo. I'll say 0.739. So that's about 0.739 for my final answer on that one. All right, so that gets us through page 6 on this. I know it might feel like it's going a little slow, got a lot of videos here, but there's a lot that goes into probability and setting it all up. We have one more video on 3.1 about cards, and then we'll get on to some other sections. But, okay, I hope you're hanging in there. Shoot questions my way if you have any. Okay, talk to you later.